Hello friends, today we will be discussing the various factors those determine acid strength. The strength of an acid here. That we know different acids have different strength. Some are weak acids, some are strong acids. There should be an explanation. Why these differences? Okay, now this is the basic reaction. That is acid A, HA. This is a bronzite acid HA. It is reacting with a base B and it is giving a conjugate base A minus and a conjugate acid HB plus. Okay, now strong acids, they have weak conjugate bases. Okay, now weak bases means what? They are stable species. Okay, and they do not want to readily share their electrons with any protons to form bonds. Okay, that is strong acids, they always have weak conjugate bases. Now weak bases, they are very stable species. Okay, now these weak bases, they do not readily share their electrons to form bonds with protons there. Now strong bases, okay, they want to share their electrons with the protons to form bonds. Okay, that is why it is strong base there. Their electron pairs, they want to readily donate that or rather form bonds with protons that way. Okay. So anything that stabilizes the conjugate base makes the starting acid HA very, very acidic, more acidic. That means the acidity, the strength of the acid HA, it is determined basically by the fundamental principle, fundamentally by the strength or stability of the conjugate base here. Okay, the more stable the conjugate base, the equilibrium is an equilibrium reaction. Okay, the equilibrium will be shifted towards the conjugate base here. That is, the more stable it is. That means there is no further reaction. That conjugate base is stabilized, means the reverse reaction does not take place there. Therefore, the acid will be very, very strong. Correct? Therefore, any factor that stabilizes the conjugate base A makes the acid, HA more acidic here. Okay. Now, the more stable the conjugate base means the equilibrium, it will be shifted towards the conjugate base here. Now, the structural differences rather between the molecules, it will profoundly alter or affect the acidity. Structural differences of molecules here. Okay, so this is the fundamental introduction. Rather, we can say the main factor is the stability of the conjugate base. So, which are the factors responsible for stabilizing the conjugate base? So, you'll have to see. Now, whatever may be the factors responsible, the general principle here, it is the same thing. Okay, now you are given two compounds and or two acids. You are asked to find out, to compare the acidity of these two compounds. Okay, what will you do? First, you have to draw the conjugate base. Correct? Then determine which conjugate base it is more stable there. Okay, the more stable the conjugate base, the more acidic the acid. This is the fundamental principle here. Now, there are mainly we can identify 4 different factors. One is the periodicity. That is the position of the element A rather in the periodic table. That is called element effects. Okay, that is element effects means I will explain to you. The second one is the inductive effects. You are familiar with inductive effects. Still I will explain. Okay, now the third one, it will be the resonance effects. Then the fourth will be hybridization effects. So these are the primarily we can say that 4 different circumstances or factors. This will influence the acidity, the strength of the acid HA here. Okay, so whatever may be the thing, the fundamental principle as I explained to you, that is the strength of the stability of the conjugate base. Okay, the more stable the conjugate base, the more acidic the acid will be. Now, first let us see what is the element effect. Element effect means identity of the particular element in the periodic table. That is the most important factor we can say, the position of the element A in the periodic table. Okay, you are familiar with the periodic table. So, the most important factor determining the acidity of HA, it is the position of A in the periodic table. That is the identity. identities of A in the periodic table. Now we can, that means the position of the element, that is called the periodicity, acidity and periodicity. That is what we are going to discuss now, acidity and periodicity. Okay, now comparing the elements in the same row of the periodic table. Now as you know, the periodic table, we have rows, that is the periods, then we have columns or we have groups here. Now we have two compounds here, for example CH4, that is a methane, and we have water. Okay, now how will you compare the acidity of these two compounds here? Now we know what water is more acidic than methane. As per the pKa values, water is more acidic than methane here. Now in both the cases, carbon and oxygen, okay, both are second row element. That means the elements in the second row of the periodic table, they are bonded to hydrogen atoms here. Therefore, now how will you compare the acidity of these two compounds? That is what we have to see. Now first thing is water. Let us see what is this HOH, water. Okay, now it is an acid. So now the pKa value of this water, it is found to be 15.7. Okay, so mildly, moderately acidic here. Okay, now this conjugate base of water, it will be HO minus. Okay, this is the conjugate base, CB, I will write in short. Here the negative charge, it is on the oxygen atom. Now if you take methane, this is the methane molecule. Now this is also an acid, so its pKa value, it is equal to 50. Now we know the smaller the pKa value, the stronger the acid. Okay, pKa 50 means it is a very weak acid. Here pKa 15.7, therefore water, it is more acidic. The strength of the acid strength for water, it is more compared to methane here. pKa 50, pKa 15.7. The smaller the pKa value, the stronger the acid here. Now in this case, what is the conjugate base? It will be, that is, loss of a proton will give you conjugate base, you know that, and gain of a proton will be conjugate acid. Okay, so this is the negative charge here. It is in carbon atom. Here the negative charge, here negative charge on oxygen, and here negative charge on carbon. Okay, so this is the difference here, because oxygen atom is much more electronegative than carbon. So an oxygen, it will more readily accept a negative charge, therefore making OH minus much more stable. Okay, because here the negative charge, it is on a more negative atom, oxygen here. Okay, so oxygen more readily accepts the negative charge, making OH minus much more stable than CH3 minus here. Now therefore OH minus, that is the conjugate base, is more stable in the case of water. Therefore water is a stronger acid compared to methane. OH minus is more stable and rather than CH3 minus. Okay, so OH minus is more stable and therefore water is more acidic. This is more acidic and this will be less acidic, correct? This is where we have to, as per the periodicity of the elements in the periodic table here. Now across a row, if you see a row of the periodic table in a period, the acidity of HA increases as the electronegativity of A increases. Now what is meant by electronegativity? So I will explain it before I discuss the inductive effects and all, So across a row of the periodic table, if you see a row of the periodic table, the acidity of HA, that is when we are going from here, that is group 1, 2, 3 up to 7. If you are just going like this, C, this is carbon group 4A, we are having here the CH, this one. Then we have NH. Then we have OH. Okay. Then we have HF. Okay. So across the row of a periodic table, that is when we are going from here, group 4, group 5, group 6, group 7 here, the acidity of HA increases because the electronegativity of A increases. Electronegativity means that is the attraction for the electrons. Okay, now fluorine. Fluorine is the most electronegative atom here compared to oxygen and nitrogen and all here. Okay, now fluorine has the greatest attraction for electrons. Therefore, HF, in the case of HF, hydrogen fluoride, it holds on the electrons. Okay, then very strongly here. Correct? Therefore, fluorine does not want to share the electrons with any proton here. Therefore, the fluoride minus, F minus, okay, it is the weakest anion. Fluoride minus is the weakest anion and the most stable anion here. Correct? Correct. This is the periodic trend here. That is HA, that is the acid, that is the group 4, 5, 6, 7. If you are just seeing here, the electronegativity, okay, the increasing electronegativity, this side, if you see, if you put an arrow like this here, this is increasing electronegativity. Correct. So, increasing the electronegativity, the acidity, it will increase the acidity also. Increasing electronegativity increases acidity. Why increases acidity? Because the conjugate base will be more and more stabilized here. Okay, now fluorine, that is what I was just discussing here. Fluorine here, in this case, it has got the greatest attraction for electrons here. Therefore, HF, hydrogen fluoride, it holds on the electrons very, very strongly. Fluorine, it does not want to share these electrons with any other proton. Therefore, fluoride anion, this is the fluoride anion. This is a very stable one. It is the fluoride anion. It is the weakest one. It is the weakest means most stable. Therefore, the acid HF here in the series, HF will be the strongest acid here. Okay, that is why comparing elements now down. Now, when we compare the elements down the column of a periodic table, this is across the row. Now, down the column, now we have HF, that is fluorine is there. Then down we have HBr. Okay, now we have HBr here. Now here also what we have to do, which is the stronger acid? Hydrofluoric acid, then hydrobromic acid, HBr. Now first we have to determine the stability. Okay, the stability of the conjugate base here. The conjugate bases are for the fluoride anion and the bromide anion. Okay, these two are the conjugate bases here. Determine the stability. Stability of the means that means it should not be reactive. That's all. It should be very, very stable. What are the factors responsible for making it very, very stable? That is more important for us now. Okay, the stability means it loses its further reactivity. Therefore, the acid continues to become very, very strong. Correct. So, the stability of the conjugate base here, fluoride anion and bromide anion. Here, what happens down the column? Not only the electronegativity. If you see the electronegativity factor, fluorine is more electronegative than bromine. But here, when you are coming down the column of a periodic table, what is important? It is the atomic radius. That is the size. Okay. Size of the atom. When the size of the atom, it is big one, is a larger one. Okay. So, the size is more important than electronegativity. Okay. Now, the size of an atom, that is, or ion. We can say an atom or an ion. That means the atomic radius, it will be more. So, as the size increases down a column of the periodic table, what happens? The negative charge, it will get stabilized because the positive or negative charge, whatever is the charge, if it is spread over a larger volume, here the size, because the volume, atomic radius is larger. Therefore, the charge is spread over, while electron density it is spread over a larger volume. Larger volume means the reactivity comes down, it becomes more and more stable. Okay, therefore, the size of the atom here, it increases down the column of the periodic table. Here the bromide, it is a larger than fluoride. The size wise, this bromide is larger than fluoride here. Therefore, in this case of bromide, this acid HBr, it is a stronger acid. Now the two important differences here that we can say between the fluoride and bromide, that is the electronegativity is there and the size. Okay, whether it is a positive charge or it is a negative charge, it is stabilized when it is spread over a large volume. Okay, so now generalizing, now we can say the acidity of HA, it increases both left to right of the periodic table across a row. Okay, now across the row of the periodic table, since the electronegativity increases, increasing electronegativity increases the acidity. Now down the column, okay, down the column of the periodic table, the size of the atom, that is the atomic radii, atom or the ion, okay, it increases, and therefore the charge is spread, the electron density is spread over a larger area. Okay, so therefore the anion, it is getting stabilized here. The bromide is larger than fluoride, simple thing. Bromide anion, it is larger than fluoride anion. So bromide is more stable than fluoride. Therefore HBr, it is acidity wise, HBr, it is a stronger acid, okay, than HF, hydrofluoric acid. Okay, now if you see, the trend will be, say, HF, then the increasing acidity, it will be like this. HF is there, then we have HCl is there, then we have HBr is there, then we have hydroiodic acid, HI is there. Therefore, increasing size, increasing acidity. So this side, this is the increasing size. Therefore, increasing acidity. This is the periodic trend, increasing acidity. Here, hydroiodic acid, it is the strongest acid because iodine, the iodide anion, or it has got the largest atomic radius or the size. Therefore, as the size increases, the electron density, it is spread over a large area here. Okay, therefore, the iodide anion, it is the most stable one here. Therefore, hydroiodic acid HA, it is the strongest acid. HI, strongest acid. Okay. So, these are the fundamental things about the trends, periodic trends we can say. So, now, here, that just we are discussing the iodide anion, it has a much larger electron cloud rather, than the fluoride anion. Okay, that is the thing. The electron cloud, it is spread over a larger area here. Iodide anion, it disperses negative charge over a larger area. So it will have a less attraction. When it is spread over a larger area, it will have less attraction for a positively charged proton. Okay, therefore what happened? Iodide anion, it is the most stable one. Most stable base, at the same time it is the weakest base. The weakest one, the most stable one in the series here. If you see all these, the acid series here of the halogens, okay, the most stable and the weakest one base in the series, it is iodide anion here. Okay, therefore the larger the size of the anion, the more dilute, will be the electron density. Okay, the electron density will be diluted. Larger the size of the anion, therefore the acid becomes stronger. Correct? Now, if you see one problem, we can give you which compound in each pair. Now water and hydrofluoric, I will give you two problems here. Now, which compound in each pair is a stronger acid? Now, if you see the water, H2O, then and hydrofluoric acid, HF. Okay, which is more acidic here? Now, both have hydrogen atoms. The hydrogen atom bonded to electronegative oxygen here, bonded to a second row element in the second row of the periodic table. That is element, the one is oxygen, the other one is a fluorine here. Now, acidity of HA, we have seen the periodic trend. What is the periodic trend here? The acidity of HA increases across a row of the periodic table. Correct? And here HF bond, it is more acidic. Why? Because HF bond is more acidic than the HO bond here. Here there is an OH bond, HO bond is here, and there is an HF bond here. So this HF bond is more acidic. HF bond is more acidic than the OH bond here, because then HF is a stronger acid than water here. Correct? Because of the periodic trend only. You see, both have the hydrogen atom bonded to a second row element, and we know the acidity of HA increases as we go across the row or the periodic table here now. Okay. Now, HF bond, it is a more acidic than. Therefore, the HF is a more acidic, stronger acid than water here. Now, if we compare these things, hydrogen sulfide and water, if we compare these two things, here also the same principle, same logic, it will apply. That is, in this case also a second row element, both have hydrogen atom bonded to the elements in the same column. It is not row. Oxygen and sulfur, it is in the same column group, same column element. Okay, S and oxygen here. Correct? Now, water and H2S both, they have the hydrogen atoms. They bonded to the elements in the same column here. Now, because the acidity of HA increases down the acidity of the HA, it increases down a column of the periodic table. HS bond, okay, it is more acidic. HS bond more acidic than HO bond here. Therefore, what happened? Hydrogen sulfide, it is a H2S. It is a stronger acid, correct, than water. Okay. Therefore, the principle here, first, to decide which hydrogen it is more acidic, first determine what element each hydrogen it is bonded to. Here, all the same thing what we have compared is H2O, HF, H2S, and all this kind of a thing. Now, what we have to see is the hydrogen. To decide which hydrogen is most acidic, we have to see the hydrogen is bonded to which atom. That is all. So, which hydrogen is most acidic means first you determine, what element each hydrogen is bonded to. And then decide its acidity based on the periodic trends here. Okay. This is how you will have to work out, Now, when we are considering another small problem, in this element effect here, I can give you now a compound, say CH3, then NH, nitrogen, CH2, say CH2, CH2, CH3. Suppose we have a compound of this nature here. Now, it contains how many these things are there? This compound is a long compound here, CH3, NH, CH2, CH2. This is hydrogen only. See, if you are having a compound of this nature, how many types of bonds are there in this one? In this compound, we have only one carbon-hydrogen bond is there. Then we have a nitrogen-hydrogen bond. These are the two different types of bonds here. Okay, in this compound. Carbon-hydrogen bond, CH bond, and there is an NH bond here. Alright. Then acidity of HA, we know it increases across a row of the periodic table. That means the hydrogen is bonded to the nitrogen, hydrogen is bonded to carbon here. Most acidic compound, which is the most acidic compound here, then the nitrogen, NH. Correct. The single hydrogen on nitrogen, it is the most acidic here. Correct. Which hydrogen is more acidic if you ask me? This is the answer here. Okay. This compound contains only carbon-hydrogen bond and a nitrogen-hydrogen bond here. Now acidity increases of HA, this compound HA acidity, it increases across the row of the periodic table. Okay, then the hydrogen bonded to nitrogen, it is the most acidic compound, hydrogen in this compound here. Okay, now this is all our discussion about this thing, element effect, that is the periodicity and acidity, that is the thing. Now next we will be discussing electronegativity, then inductive effect. Then inductive effect, how the conjugate base is getting stabilized. You see, that is our question here. Now what is going to be electronegativity here? So we know electronegativity, it is the electronegativity and bond polarity. If you see, that is the degree of attraction for an electron, in the bond. That is, a bond means a covalent bond here. Say XY, we have a covalent bond XY, and this covalent bond is formed by the sharing of one electron each from each atom here. Okay, so it's a 2 electron bond here. Now electronegativity, it means the measure of an atom's attraction for electrons in a bond here. Okay, that is, it is a measure of an atom's attraction for electrons in a bond here. So it is actually we can say it is an attraction for the electrons here, that is in the bond, correct? So in the periodic table, if you see, the electronegativity increases, we have seen now, across the row of the periodic table, because the nuclear charge, it will increase here. Then electronegativity decreases down the column of the periodic table as the atomic radius increases, therefore pushing the valence electrons farther from the nucleus here. So this is the most electronegative element. We see, if you see the periodic table closely, we can see the most electronegative elements, they are located at the upper right hand side of the periodic table, and the least electronegative elements, they are located down the lower left hand side. First thing is upper right hand side, this is lower left hand side. Okay, lower left hand side we can see least electronegative elements. Upper right hand side we can see the most electronegative elements. Now, so electronegativity, this is the electronegativity, it is the a degree of attraction for the bonding electrons here, correct? The measure of the attraction for the bonding electrons by an atom, that is the thing, electronegativity here. Okay, now electronegativity values, they are relative, it is not an absolute value. Relative value means compare. Now we have two atoms here, X and Y here, which is more electronegative, that is, which atom has got more affinity for electrons, the attraction for electron, which atom has got, then we say that atom is more electronegative, the other one is less electronegative. Less electronegativity means it is more electropositive. One is electronegative, other one is electropositive here. Therefore electronegativity values, they are relative. Okay, so it is only used for comparison purposes. Okay, electronegativity is being only for comparison purpose we are using here. So one atom is more electronegative, that means than the other. That means if it attracts electrons more towards itself, okay, and the other one is less electronegative, means it doesn't attract, it doesn't want the electron, it is giving up, it is repelling the electrons here. Okay, so therefore it is more electropositive. We can say it is less electronegative, or it is more electropositive. Okay, now these values, electronegativity values, they are used as a guideline. It's a guidance value, okay, to indicate whether the electrons in a bond are equally shared. Now the sharing of electrons here, now we have seen XY, it is a covalent bond here. This covalent bond, whether these electrons are either, the two possibilities are equal sharing, unequal sharing. Okay, so equally shared, it means if the atoms are of same electronegativity, the electrons in the bond, it will be shared equally. So if the electronegativity is different, one is more electronegative than the other, then the sharing will be unequal. So when the unequal sharing is there, so it's a guidance value, electronegativity. Okay, so now if the unequal sharing, say for example, if there is a bond here, unequal sharing is there. Now CC bond if we say, CH bond if we say, these are all equal sharing of the electron density. Carbon-carbon bond is equal sharing. Okay, then there is no problem here. Equal sharing means there is no problem. The bond is not polar, non-polar bond. Okay, now here carbon-hydrogen, the electronegativity difference between carbon and hydrogen, it is negligible, not much. Therefore, this CH bond is also non-polar usually. Okay, now if there is the electronegativity difference is there, the bond becomes polar here. Polar bond, we call it polar bond, since the electronegativity difference between two atoms. Say for example, if you have carbon oxygen, this bond is there. See, carbon is less electronegative than oxygen here. So bonding between different two atoms of different electronegativity is here. Okay, it will result in an unequal sharing. That is equal sharing. This is unequal sharing of the electron density here. Okay, unequal sharing of the electrons here in the bond. Therefore, CO bond, it is a polar bond here. So the bond is polar, or we can say it is polar covalent. Okay, the bond is said to have a dipole. We can say the bond, it will have a dipole. That means the charge separation, the dipole, or we can say charge separation. So how will you represent this charge separation here? Now this carbon, okay, like this oxygen, correct. Now this, there will be a partial positive charge here, there will be a partial negative charge here. Okay, this is the thing, that is, this is an electron deficient site and this is an electron rich site. So there is another way of representing it is by an arrow here. An arrow, this head is pointing towards the electron rich site here, and arrow with a perpendicular line. That is the way this dipole is represented, correct. So therefore, the direction, we know the polarity. Okay, the direction of the polarity in the bond, it is indicated by this arrow, correct. Now head of the arrow and the tail of the arrow. Okay, head of the arrow, it is pointing towards the more electronegative atom, and the tail with a perpendicular line, it is positioned at the less electronegative element, correct. Or we are using partial positive charge and partial negative charge here. Okay, now after this thing, let us see what is meant by an inductive effect. Basically, inductive effect means so this is a very important phenomenon. It's a permanent effect in a molecule. Inductive effect, permanent polarization. Inductive effects means just like we are explaining, unequal sharing, covalent single bond. Inductive effect is usually along the single bond, single sigma bond or single covalent bonds here. Okay, so this is the fundamental thing here. Inductive effect, the covalent single bond between unlike atoms. Okay, the electron pair forming the sigma bond, it is never shared equally. Unlike atoms, that is, we have an atom X and we have an atom Y. If we take it like this, okay, that is the covalent single sigma bond between unlike atoms here. The electron pair, there is a 2 electron bond here, that is electron pair. It is forming the sigma bond. It is never shared absolutely equally between the two atoms here, because here because this single bond between unlike atoms means atoms of different electronegativities. One atom is of a higher electronegativity and other one is of a lower electronegativity. One is high, other one is low. Okay. Therefore, electron pair forming the sigma bond, it is never shared absolutely equally between the two atoms. Now, it tends to be attracted a little more, okay, towards the more electronegative atom of the two here. That is, there is a tendency, there will be, suppose here X and Y, if X is less electronegative and Y is more electronegative, there is a tendency for displacement, electron displacement here, okay, towards the more electronegative atom. There here, the electronegativity of Y is higher than X. Okay, so electronegativity of Y, it is higher than X. So in this situation, there will be a tendency for slight displacement towards the more electronegative atom of the two. Now, if you are having a carbon chain, say C, 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 then we have a chlorine atom here. Okay, this is C1, C2, C3. What happens here? Chlorine has a greater affinity for electrons. Okay, it is more electronegative than carbon. Therefore, the electron pairs forming the covalent bond between chlorine atom and C1, that is the C1Cl bond. There is a bond like that here. Then there is a bond between C2, C1. Then there is a bond between C3, C2 here. Okay, there are three types of bonds here, C1Cl or ClC1 we can say. I would rather write it like that here. That is a bond between ClC1. Then we have C2C1, then C3C2. Correct? The three bonds are here. Now, here the chlorine has a greater electron affinity than carbon. Therefore, the electron pair forming the covalent bond between the chlorine atom and the C1, it will be displaced towards the chlorine atom. Correct? Now, this causes the chlorine atom to acquire a small negative charge. Okay, like this, we can say, if you are having a bond like this, so this chlorine, it will attain a partial negative charge. Okay, that is chlorine atom to acquire a small negative charge and C1, carbon 1, a small positive charge. Correct? This is how it is. We can represent it in this fashion here. That is, this is the inductive effect here. Therefore, chlorine, it is withdrawing the electron density here. Correct? Like this we can say. Electron withdrawing inductive effect it is called. Therefore, C1 is positively charged. It will attract itself the electron pair forming the covalent bond between C1 and C2. Okay, there is now C1 is positive. Therefore, it will attract the electrons here. This bond electron C1 and C2. Then C2 will become positive. Then it will attract the electron between C2 and C3, that bond here. Like that, it goes along the chain here. That is along the sigma bond, single sigma covalent bonds here it will go. But it will, the chlorine is the source here. Now, as the distance increases, this attraction for the electron, it will also come down here. That is C1, the positive charge will be higher than on C2 and C3. When it comes to C3, it almost becomes negligible. Okay, so the charge will be smaller than on C1 here. Then the effect of the chlorine atom, it has been transmitted. When it is transmitted through C1 to C2, similarly C3 acquires a positive charge, that will be a smaller charge than that on C2. So this type of electron displacement along the chain, it is known as inductive effect. Okay, electron displacement along this carbon chain, it is known as inductive effect. Now, in the case of an alkyl chloride, that is what we are just representing here, alkyl chloride, C chloride here. Okay, so this is the inductive effect here. Correct? Therefore, here there will be a partial positive charge and here it will be a partial negative charge. Electron density tends to be greater near chlorine atom than the carbon as the chlorine is more electronegative. Okay, so this is the way we are representing it, inductive effect. We are representing it in this fashion here. Okay, now we can say the most atoms and groups attached to carbon, they exert such an inductive effect in the same direction of chlorine. Okay, now that is they are electron withdrawing, more electronegative than carbon. Being more electronegative than carbon, it is electron withdrawing inductive effect. Okay, so electron withdrawing inductive effect, because of the difference in electronegativity here. So this order will be, say, nitro group, it will be more electron withdrawing, or fluorine, then we have chlorine, finally we have bromine and all this kind of a thing. It will go, finally it will be CH3. This is the series here. Okay, the order, inductive effect may be due to atoms or groups here. This is the order of decreasing inductive effect. Okay, therefore, NO2 group, it is having the highest inductive effect. Then comes fluorine. So this side, if we go, this is decreasing inductive effect. Okay, decreasing inductive effect here. Okay, now how will you measure this inductive effect? Briefly, I will tell you how will you, the measurement, inductive effect measurement of relative inductive effect. Suppose we have a compound here. So hydrogen, we are using it as a reference, standard here. Okay, we are using hydrogen as reference. Correct. Now in a compound, say for example, if you are having a compound of this nature, Cr3H, here R is the alkyl group here. Correct. R is an alkyl group, Cr3H. So measurements of relative inductive effects, hydrogen is chosen as the reference in a molecule of this nature. Correct. Now suppose when we are replacing this hydrogen, okay, we are just replacing this with a Z, another group here. Okay, and see the electron density in the Cr3 part of the molecule here. Now we will get two situations. Correct. Either the electron density in the Cr3 part will be less than in Cr3H, or the Cr3 part electron density will be more here. Okay, if the Cr3 electron density, it is less, then what happens? The Z is withdrawing the electron density there. Okay, here there are two situations. One is Cr3 Z. You see, there are two possibilities here. One, electron density will be less and or more. Okay, these are the two possibilities. I just mark it here now. This is possibility number one. This is possibility number two. That is the electron density in the Cr3 part. When we are replacing the hydrogen with a group Z here, Z is the group. Now we are seeing the electron density in the Cr3 part of the molecule. If the Cr3 part, it is the electron density less, the assumption is the Z is withdrawing the electron density. Okay, Z is considered to be electron withdrawing, electron attracting. Electron withdrawing. So this electron withdrawing, it is a minus I effect. It is known as minus I effect. These are the name nomenclature given by scientists in Gould. Okay. Now in this case, the electron density in the Cr3 part, it is greater. Okay. Electron is going in this direction, mean this is due to electron repelling or electron releasing character of Z here. This is known as plus I effect. Electron repelling. Okay, effect, that is plus I effect. Okay, whatever it is there, one is electron withdrawing. The nomenclature is not that great. We can say the electron withdrawing inductive effect as well as electron repelling. Electron repelling means, electron releasing, we can say. Correct. These are the two types of inductive effects here. Now, all inductive effects are permanent polarizations. All inductive effects are permanent polarizations in the ground state of the molecule. not excited state, permanent polarizations in the ground state. Okay, so it will decrease rapidly as the distance from the source increases. Okay, now from the practical point of view, we can say it can be ignored after the second carbon, correct? Now, even though the electron pairs are permanently displaced, it will remain in the same valence shells here, correct? So, this is the fundamental principle about inductive effect here. Now, I will explain to you with some examples. So, acidity of HA, as we have seen, acidity of HA, it is influenced by the presence of electronegative atoms. I will clear this page here. So now we can compare the acidity of two compounds here. Okay, the two compounds are, one is CH3, CH2OH, one compound of this, that is our ethanol here. Okay, that is, if the electronegative atoms are there, the acidity of HA, it is influenced by that thing. Okay, now we will be comparing the acidity of, say, this is ethanol. Then we have a compound of this nature, that is CF3, CH2OH. So this is 2,2,2 trifluoroethanol. Okay, if we compare the acidity of these two compounds here, that is ethanol and 2,2,2 trifluoroethanol, these are the two different compounds having an OH group here. Okay, that is this pKa value. We can see ethanol is having a pKa value of 16, and this pKa value, it is 12.4. That is, which is more acidic now? Smaller the pKa value, the higher the acidity. That is, the greater the acidity, more acidic. Okay, therefore CF3CH2OH is more acidic than ethanol. How will you explain this? Now, the principle here is, now this is a stronger acid. This is a stronger acid here. Now first draw the conjugate base. Okay, and then determine which conjugate base. That is a fundamental principle here. Draw the conjugate base, then you determine which conjugate base will be more stable. Okay, then both bases here, it have a negative charge on it. Which are the conjugate bases here? So this is the conjugate base of ethanol. This is the conjugate base of ethanol, and this is the conjugate base of trifluoroethanol here. Okay, now in the first one, that is the ethoxide anion, CH3CH2O minus, that is a conjugate base of the ethanol. Okay, now both the bases, it has got a negative charge on an electronegative oxygen atom. But here in the second one, the anion, it has got 3 additional electronegative fluorine atoms. Okay, now the fluorine atoms here, they withdraw electron density from the carbon to which they are joined. Okay, or they are bonded together. Correct? So, making it electron deficient. So here I can show you. Say, now this is the fluorine atom here, CF3, then we have CH2, O minus. Okay, this is the conjugate base here. So there will be electron withdrawing here. Electron will be, CF3 withdraws the electron density. CF3 group, it is withdrawing the electron density from the oxygen side here. Okay, therefore, this is more stable here. So this is the way it is withdrawing here. Electron withdrawing. Every direction it will be withdrawing here. This fluorine and all, it will withdraw the electron density here, correct? Like this it will go. Okay, therefore, CF3 withdraws electron density, then stabilizing the conjugate base. Okay, this is the conjugate base, this is the CB, this is CB, conjugate base here. Okay, so in the first case, CH3CH2O minus here. Okay, the electron deficient carbon, in the second one, the electron deficient carbon atom, it pulls electron density through the sigma bonds, correct? From the negatively charged oxygen atom here. That is what is happening here in this conjugate base here. In this conjugate base, electronegative oxygen atom here. Okay, this electron, there is an electron deficient carbon. So here there will be a partial positive charge. This is a partially positive, and here all partially negative. We can see here. Okay, like this. That is the electron deficient carbon atom. It is pulling the electron density, okay, through sigma bonds. All through sigma bonds, okay, from the negatively charged oxygen atom, correct? Negatively charged oxygen. So in that process, what is happening? The negative charge, it is stabilized, stabilizing the negative charge. Negative charge stabilized. Therefore, it is becoming, more stable. Once it is stabilized means, negative charge is stabilized means this conjugate base is more stable. Therefore, the acid corresponding acid here, that is CF3CH2OH, it is a stronger acid. Okay, that is how we have to explain here. Now CH3CH2O minus, it has no additional electronegative atoms to stabilize the conjugate base. Okay, here there is no additional factors here. Okay, there is only a negative charge here. There is nothing to stabilize this negative charge on the oxygen atom here. But here, in this case, the negative fluorine atoms, they stabilize. And same is the case with the chlorine, chlorinated acetic acid. The same system, that is acetic acid, CH3, COOH, here, CCl3, if you take it. Okay, this chlorine atom and all, it stabilizes. Okay, the carboxylate anion, CO minus anion there. Therefore, this will be more acidic than acetic acid. Like that, we can keep explaining here. Okay, now inductive effect here, it means the pull of electron density. Electron density is being pulled through sigma bonds. Okay, it is caused by the electronegativity differences of the atoms. Okay, here we have the carbon, oxygen, fluorine, etc. So the fluorine is more electronegative. Therefore, inductive effect, it is the pull of electron density through sigma bonds. It is caused by electronegativity difference. Okay, now electron density, it is pulled from the negative charge through sigma bonds. Okay, by the very electronegative fluorine atoms here. Correct? So it is called electron withdrawing inductive effect. Okay, now the three electronegative fluorine atoms, they stabilize the negatively charged conjugate base. Okay, that is the three negatively charged, the three electronegative fluorine atom. Three electronegative fluorine atoms, correct, stabilize the negatively charged conjugate base of this. This is the conjugate base, negatively charged conjugate base. It is stabilized by the three fluorine atoms here. Okay, electronegative fluorine atoms. Okay, therefore, this acid, particular acid, CF3 acid, it is a stronger acid here than other one. Okay, therefore, the acidity of HA, it will increase with the presence of electron withdrawing groups in A. Okay. So this is our inductive effect and acidity. Okay, so thank you very much for listening.